Hey everyone, welcome back. Today we are diving into a classic stress concentration problem in Abaqus, which is modeling a plate with a hole. This is a crucial concept in structural analysis, and we'll walk through how to set up, run, and analyze this simulation in Abaqus. We're working with a rectangular 2D plate made of mild steel, 200 mm long and 100 mm wide, with a 10 mm diameter hole at the center. The plate is fixed from one end and being pulled out from the other end with a uniform pressure of 1000 megapascal. Alright, let's jump to Abaqus and begin the simulation. Okay, I chose a standard explicit model, and just like before we are going to start with part. The part should be 2D planar, deformable, shell, and the approximate size should be something around 400. We have a 2D model, so we chose 2D, and the extrusion doesn't matter here. I would like to rename it with plate with hole, and click continue. Then I create a rectangle and add the dimensions. This guy should be 200, press enter, zoom out a little. This guy should be 100 and enter. The next important thing is to create the hole or the circle. Just keep in mind this tiny line on the top should be either on the top, on the bottom, or on the right or the left side. You should not keep it in the middle because it would mess with the meshing. So I would like to put it here to in order to add the diameter. You have to click on somewhere on the circle and set the value of 10 for this guy, and we have to select the distance between that. This one should be 100 because the hole is in the middle, and this one should be 50, which is 50. That's cool. Click done, and we have our plate. Next, let's move on to defining the material's properties. We go to the property module, we click on create material. Let's rename it with steel. From the mechanical properties, the elasticity and elastic. Young's modulus should be 210,000 megapascal, and the Poisson's ratio should be 0.33. This is okay. Now it's time to create the section. If you click on create section, just keep in mind you have to choose a solid homogeneous, though we are using a 2D plate. I explain it now. Using a solid homogeneous section in this case ensures that the mechanical properties of the material are uniform throughout the plate, enabling accurate representation of how stress concentrates around the hole under uniaxial tensile loading. In other words, it simplifies the setup without compromising the fidelity of the stress analysis. So we choose solid homogeneous, and we create and continue, and it should be the steel. We would like to check the plane stress, and the thickness of the material should be 2. And now we have to assign the section. We select the material, the plate, we click done, and it says the section 1 from the section, and we click OK. Now it turns green, which means the material is assigned. Now the materials is assigned and the property was created. It's time to go to assembly. Here I click on create instance, plate with hole. This time I would like to put it on independent mesh. It doesn't matter. And the assembly of the model is over. Now it's time to go and create the step. Here I would click create a step, initial static general, continue. We would like to check this analgium, and the increment should be 100,000. The initial, let's say 0.05, 1e minus 9, and let's put this guy as 0.1, and it's over. Now it's time to go to define load and boundary conditions. So I click on load. Here we have create boundary condition. First we have to encast the bottom part. So we click on this one, we select this edge, click done, encast, OK. Now you see that the boundary condition is applied, and we would like to place one more boundary condition on the upper region. Here from displacement slash rotation we create we use this edge, click OK. So the model is just going just like moving in y direction, so we don't need x direction. U1 representing the x direction, U2 is y direction, and UR3 is rotation in the z plane. So I would like to close this one by clicking on U1 and putting a value of 0. You ensure that the material is not going left and right. So I click OK on this guy, and as you see here the boundary condition is applied, and the last thing to do is to apply the force, or we would like to have it pressure. Continue, select this one, click on done, and the magnitude should be -1000 because it's going to be tensile. Here you see the direction of the load. Okay, since the load and boundary conditions are applied, it's time to go and create the mesh. Let's set up the mesh now. For this model, we need to ensure the mesh is refined around the hole to accurately capture the stress concentration. So I would like to create another circle. So we can click on partition face, sketch, and we can create a circle here. Like this size is approximately okay, and we want to create some lines. I create a line and press escape. Then I create another line, and yes, it's good. And there we go. As you see here, we have two circles, one which is the hole and the other one is the outer circle. And why was that important to put the point here on one of the main directions? Because if the point was here, this edge would be divided into two edges. So without wasting any time, we would like to go and create our mesh. So we click on seed edge, and by holding shift we can select these two guys, click done, put it on by number, set the value of 25, and these two guys must be 10. Now it's time to select these 4 edges. We set a value of 4 for them, and for each one of quarter of circles we would like to put the value of 6, and done. Now we click on mesh part, yes, and now we see we have a good mesh, and we are good to proceed to the final stage, which is defining a job. So I create a job, let's say stress concentration, continue, okay. From here we can submit the job. Let's monitor it. And it is completed. So we're good to go to the results section. By here plotting the contour, we see that the highest stress is 242 megapascal and happening in the edge, like on either edges, and we can see that the value, we can see the contour option, and from the limit show location we can see the exact location. Here it is the highest value for that. And one thing we can do is to plot the stress and strain. So from here we choose ODB field output, and here from integration point we select the unique nodal, and here we have to select LE22, and from stress component we should check S22, and from the elements and nodes we edit the selection. For instance, we select this one to see how it changes. We can plot it here, but by plotting we see here stress and strain are here, and this is time, and we want to change that. So once more create on XY data and operate on XY data, continue, and from combine we first select the strain, then the stress, and we plot it, and there we go. We have a stress versus a strain here, and we can export the plot if we want. From here the XY plot is here, the chart is it should be here, and this is the XY data, and by here by edit we can select and copy and paste it to an Excel file if you want, or doing anything what you want. And that's it for this simulation. You've just modeled a classic stress concentration problem using Abaqus. If you found this video helpful, don't forget to like and subscribe for more detailed tutorials. We'll continue to explore more advanced models in the upcoming videos, so stay tuned.